This lesson is going to be a lecture on heat of combustion. To start off with heat of combustion, we first need to address what actually a combustion reaction is, where this heat is actually being produced from. So what is a combustion reaction? It is a reaction in which a fuel, that's almost always a molecule, combusts or burns. So any chemical reaction where you see burning happening is a combustion reaction. And you might remember from your own experiences that in order to burn something, it requires oxygen. So oxygen will always be a reactant and produces carbon dioxide and water. So therefore, carbon dioxide and water are always going to be the products. I have here 3 different reactions, chemical reactions. Take the time and determine which one of these is a combustion reaction. So reviewing on what we had talked about earlier is that we have chemical reactions that sometimes release energy and sometimes they absorb energy, and it has a lot to do with what chemicals there are. And just as a reminder, if they are absorbing energy, we actually write the amount of energy they absorb on the reactant side. Whereas if they release energy, we always write it on the product side. So we're going to be setting up a combustion reactions. And in this case, this is what we call a basic calorimeter. We have a burner that contains ethanol. And let's say, for example, there are 5 grams of ethanol in here. And ethanol is C2H6. All right. And above that flame, we have a beaker of water or a can of water. And in that can, there is a thermometer. And let's say, for example, we have 10 grams of H2O in here. All right. So just a note, we had worked on this earlier before or had mentioned it earlier that 1 gram of water equals 1 milliliter, or 1 milliliter has the mass of 1 gram. That's only unique to water, nothing else, okay? And so when we work through some of these combustion problems, you're going to notice that it might say, oh, you have 10 milliliters of water, in which case that's the same thing as saying 10 grams of water, okay? And keep in mind, it's only unique to water. So I have this combustion reaction where I have a fire burning. That is because ethanol is reacting with oxygen and producing carbon dioxide and water. And as a result, it releases energy. All that energy, and I'll do little squiggle lines, is going to be transferred into this can with the water. And so we can determine how much energy a fuel releases by how much this water heats up. So let's look at a couple of examples. Let's say, for example, I have my water in my can, and what happens that if instead of having 5 grams of ethanol that I'm burning, that this time I'm burning 10 grams of ethanol. What do you think is going to be happening to that water temperature? And we'll make the assumption we still have 10 grams of water. Let's try another one. In this case, I have my original 5 grams of ethanol. But this time, instead of having 10 grams of water, I actually have 20 grams of water. How do you think that's going to affect the temperature of the water? So one of the things that we notice is that the amount of energy it requires to heat water depends on how much fuel you use and how much water you're heating. And so the more fuel you use, the more energy is produced, and that means that you have an increase in water temperature. The more water you have, that means that it requires more energy to heat that water. And when you look at those relationships, you will see that we can create an equation that is Q equals MC delta T. Okay, so we can talk about this energy absorbed or transferred as the energy going into the system. And we saw that if we have more water, that means that it requires more energy to be transferred in order to have the temperature change, have that temperature change that we expect. On the other hand, we can look at it in another way where, so that's a direct relationship, they are opposite each other on the equation. If I have a greater amount of energy, so if I transfer more energy into the system, how does that affect the temperature? Well, it increases the temperature. You find a greater increase in temperature. And so that is also a direct relationship. More energy, greater increase in temperature. And again, that is why these two variables are on opposite sides of the equation. So just as a navigation going through what these variables mean, when we deal with mass, we deal with mass of water. I'm going to introduce this concept of specific heat. Each chemical has the ability to heat up 1 gram. It has the ability to heat up 1 degree Celsius for every gram that it has. Now, some things don't need a lot of energy to get hot. For example, if you think of a metal pot, if you put a metal pot onto the stove, it very quickly heats up. Or if you put a metal spoon into a hot cup of water, you'll feel that that spoon quickly gets hot. But other things take a lot longer or take a lot more energy to actually heat up. A plastic spoon, for example, if you put it into a hot cup of water, that doesn't actually heat up as fast or as much as a metal one. And so for that reason, each material has a different specific heat depending on how much energy it requires to heat 1 gram of that substance 1 degrees. And we call that specific heat capacity, and so we use that letter C. So a couple of general concepts. When we have a value that is going to be negative, a Q value or a delta H, and we can use them interchangeably, a negative value means that energy is leaving the system. If we have a positive value, that means that energy is entering the system. So let's go ahead and go through an example. So for this example, we're going to be focusing just on the water. So let's say I have 20 grams of water, and this burner is more or less releasing a total of 40 kilojoules of energy into the water. So we've been burning this ethanol, that heat moves up, it transfers its energy into this water. What we would like to know is what is the change of temperature. Okay, so first of all, if you're heating up water, you're expecting that the temperature is probably going to increase. So we're going to be using that Q equals MC delta T equation. Remember, Q stands for how much energy is transferred in or transferred out, depending on if it's a negative or positive sign. M stands for mass, C stands for specific heat capacity, and delta T stands for a change in temperature. And one of the things that you notice over here is water has a unique specific heat capacity of 4.18 joules for every gram delta T. Okay, this is a number you do need to memorize. That means that for every 1 gram of water, to increase the temperature by 1 degree Celsius, it requires 4.18 joules of energy. And so since we are heating up water, we know that our specific heat capacity is 4.18 joules per gram delta T. We know that our mass of water is 20 grams. And we know that the amount of energy transferred into the water is 40 kilojoules. So in this case, what we're going to be doing, and actually let's change that into 40 joules, just because we're going to have issues with our units, okay? So in that case, if I have 40 joules of energy going into the water, I'm going to plug all those numbers into my equation, and I'm going to find that I will have a temperature change of 2 degrees. So that means if it happens to be 25 degrees Celsius to start off with, it's going to be 2 degrees warmer at the final temperature. So it'll be 27 degrees Celsius. Okay, so a couple of things to note. This Q value is always in joules. It's not in kilojoules, and that's why I didn't make that change. Let's try one more example. In this next example, we still have 20 grams of water, but in this case, the temperature changed 5 degrees Celsius. So I want to know how much energy was transferred into this water to now change the temperature, not 2 degrees, but 5 degrees. Same situation, we're going to be using that Q equals MC delta T, in which case I plug in my numbers. I know I have 20 grams of water. Because I'm using water, I will use this as my specific heat capacity, and this time the temperature changes 5 degrees. So plugging this equation into my calculator, I'm going to calculate that it takes 418 joules of energy to increase the temperature 5 degrees. Now we can do any of these specific heat capacities, or these what we call enthalpy equations, with any material. We've always been using water. Whenever we use water, we always use that 4.18 joules per gram change in temperature. But in some cases, we can actually use different metals. So what happens in this case where I have gold, and I'm going to want to raise its temperature from 22 degrees to 85 degrees, and I have 15 grams of it. Again, I'm going to plug in my variables in my equation. Keep in mind that my delta T is always final temperature minus initial temperature. In this case, it gives me a positive value. And when I plug these in, note that I'm not putting 4.18 as my specific heat capacity. Instead, I'm putting in the specific heat capacity for gold. I'm not working with water, I'm working with gold, so I have to have it be unique to gold. And I will always give you the specific heat capacity. So when I work through the calculations, it looks like I need 120 joules of energy to enter that gold in order for it to increase its temperature. And because energy is entering the gold, this process is endothermic.